and look at mechanical forms of work. The traditional definition for work is just basically an integral of a force, integrating a force acting over a distance, right? So if we go ahead and we integrate that, and of course if the force is constant, we get that it is force times distance. Now, let's take that definition and expand it a little bit. What if we take this and we multiply it by 1? What I mean by 1 is area over area, right? If I multiply that by area over area, which is 1, I can go ahead and I can take the area on the denominator, put it underneath the force, multiply that by the distance that the force acted on times the area on the numerator. This becomes change in volume, and this is pressure. So another way to look at it is a pressure acting over a change of volume. And that's basically going to be one mechanical form of work that we'll look at is pressure change over a pressure acting over a volume change for constant pressure. So if you look at it from that premise, the requirements for work is an interaction between a system and its surroundings. There must be a force acting on the boundary, and the boundary must move. That is where this definition comes from, is that if there's going to be a volume change, there has to be a pressure acting on the boundary. So that can be in the form of spring work, right, where we have spring work, again, where this delta, this Greek lowercase delta, basically means a path-dependent function, equals force times dx, where the d, the differential, is in regards to a state-dependent variable. So when the length of a spring changes by a differential amount dx under the influence of force F, we get this function to describe the amount of work done. So to determine the total work, we need to know the functional relationship between force and distance. Typically, for a spring, for a linear elastic spring, the displacement is proportional to the force. So the force is going to be some spring constant times x. So if I take that and I integrate, replace the force in this equation here, and then integrate, I get the integral of fx dx between two different points on the spring. I get that the total force acting over the distance is going to be the k constant, the constant of spring k, times the distance at the end of the process squared minus the distance at the start of the process squared. So that would be the total work done for a linear spring. There's other forms of work that are non-mechanical, right? Some work modes encountered in practice are not mechanical in nature. Non-mechanical work can be treated in a similar manner by identifying a generalized force acting in the direction of a generalized displacement. So the differential work is determined by, again, some force acting over a distance. So examples would be electrical distance or electrical force or magnetic, right? And so the generalized version of force, for example, the equivalent of force for electrical work is voltage, and the equivalent in magnetic work would be magnetic field strength. The generalized displacement would be electric charge for electrical work, and it would be magnetic dipole moment for magnetic work. So let's come back and dig a little bit deeper into the first law of thermodynamics. All right, we talked about this in part. Let's start to kind of bring it together a little bit. The first law provides a basis for studying the relationships among various forms of energy and energy interactions, right? We talked about that. It is based on the conservation of energy principle. Energy can neither be created nor destroyed. It can only change form. And that is the whole point of a first law analysis. A first law of thermodynamics is looking at energy interchanges and analyzing or quantifying its change in form. A consequence of the first law is the existence and definition of the property total energy. right? The total energy of a system. The first law is the whole premise on regarding an energy balance. The energy balance is stated as the following. The net change, increase or decrease, in total energy of the system during a process is equal to the difference between the total energy entering and the total energy leaving the system. And in thermodynamics, energy can only transfer three ways, and three ways only. Always, only three ways. Energy can transfer by mass, right? So if I have a mass going into the system, that mass is carrying with it energy. So I have mass energy in and out. That would be for a control volume, right? For an open system, because a closed system, mass does not cross the boundary. But for an open system, mass does cross the boundary and carries in and out energy. That's number one. Number two, work. And then number three, heat. Energy can only transfer three different ways: heat, mass, and work, period. That's it. No other way. And this is the whole first law in one equation right here. What we're going to be doing in the next several chapters is just a reapplication of this same thing, expanding this equation into a form that is appropriate for the specific problem sets that you will be solving. And here it is. It is the total energy in minus the total energy out equals the total change in energy of a system. Or if you want to expand it, it would be the total energy in by heat, mass, and work minus the total energy out by heat, mass, and work equals the total change in energy of the system, which is internal plus kinetic plus potential. This relationship is referred to as an energy balance, and the relationship is valid for any system, always any system undergoing any process. This is the premise for a large part of this class. And for the next month or so, we're going to be concentrating solely on different uses of this equation. So why don't we go ahead and take this and expand it and look at each of the components here so that we can better understand how to quantify E in, how to quantify E out, how to quantify delta E. So let's take this one first, and let's take it to the next slide and write it out. Delta E. Delta E, we'll call it delta E system. The energy change is the difference in total energy between the initial and the final state. E final minus E initial, or E2 minus E1, right? State 2 minus state 1, which has to equal the change in internal energy of the system plus the change in kinetic energy of the system plus the change in potential energy of the system. Energy is a property. Energy transfer is not a property, but energy itself is a property. And the value of a property does not change unless the state of the system changes. So that means E for the system doesn't change unless a process occurs that causes the energy to change. Energy can exist in many forms. Internal energy, right? Kinetic, potential, electric, and magnetic. And their sum constitutes the total energy E of a system. In the absence of electric, mechanic, and surface tension effects, right, the change in energy of a system during a process is the sum changes of its internal, kinetic, and potential energies. And here is basically how we are in thermodynamics going to quantify this term. This term, which is this term, the change in energy of the system, right? We're going to look at the three different parts. This is part 1, part 2, and part 3 of universal analysis. We're going to look at delta E. So let's take that. Let's slap it on the slide here. Change in energy of the system, right? This is the energy inside the system boundary, the change in energy inside the system boundary. I'm taking this slow and I'm repeating myself several times because we need to understand we can take the first law, E in minus E out equals delta E system, and treat each part of it differently. So now we take the delta E system, we're putting it on this slide, we're looking at that term only. We're not looking at E in and E out, only delta E right now. That has to equal the change in internal energy of the system plus the change in kinetic energy of the system plus the change in potential energy of the system, right? So how do you quantify the change in internal energy of the system? Well, it's mass of the system times the specific internal energy at state 1 minus the specific internal energy of state 2. And we'll talk later about what internal energy is and how to quantify that. But this is a state-dependent function. If I know two properties at state 2, I can find U2. If I knew two properties at state 1, I can find U1. And I can find the change in internal energy. Same thing, delta KE. How do I find that? Well, it's 1/2 mass times the velocity of the system at state 2 minus the velocity of the system at state 1. What's delta PE? Delta PE would be mass of the system times gravity times the height of the system at state 2 minus the height of the system at state 1. Right? So all that stuff is happening to the system that causes it to change velocity, position, and internal energy. Now, when I look at a stationary system, right, what's happening? Stationary system is just what it means. It means it is not moving. If it is not moving, that means there's no change in kinetic energy and there's no change in potential energy. So that means this delta U term is equated to be only equal to delta U. All right? Okay, now that's delta E. Now what I'm going to do is we're going to take E in and E out. We're going to take that out of the equation and quantify that one. So let's take that equation. Let's advance to the next slide past where we were and figure out how to quantify that one. So all the mechanisms of energy transfer are encapsulated in E in for going into the system and E out for leaving the system. And that energy transfer, this is not energy itself, this is energy transfer. This is energy in the process of moving from one point to another based on the process. These are path-dependent functions. En depends not only on En depends on how the process is occurring, right? And that's a sum total of energy transfer by heat, by work, and by mass, all added together into this one term En. And then E out is the addition of energy transfer by heat, by work, and by mass, all added together to be this term. So all these energy interactions, E in and E out, are always and only, on every circumstance, only recognized at the boundary. So taking these three forms of energy into account, the energy balance can be written as following. E in minus E out equals, excuse me, I don't know why it keeps coming up with that elongated line. Let's correct for that real quick. Okay, so E in minus E out has to equal the Q heat in minus the heat out plus the work in minus the work out plus the energy being carried into the system by mass minus the energy being carried out of the system by mass. And if you want to write this more compactly as it was earlier, it is E in minus E out equals delta E system. The basic, most fundamental, reduced, compact, written version of the first law. Now this can be written in both rate form and per mass form and differential form, right? Rate form meaning if I have a process that's occurring where I have energy in watts being transferred constantly into the system and energy in watts being constantly transferred out of the system and causing some increase in energy of the system per time, right? I would write it in that form. If it was per mass, I would write it in this form. Or in differential form, where I would have the state-dependent variable, right, delta E system, written as dE, and the path-dependent variables written in delta form. Those are the different forms of how I can write my first law. All right, let's try something here. Let's try some sort of an analogy here. This is called the farmer's pond analogy, and I think it's pretty effective. So I'll do my best to try to explain this without being there in person for you to be able to see my gestures. And so let's look at this. I'll just read it out loud and then I'll go to a diagram to kind of explain it more. Let's consider the following analogy here. A farmer owns a pond fed by a stream and drained by another. The pond also receives water from rainfall, and it loses water by evaporation. So let's consider the pond is a system of interest, and the water within the pond is analogous to the internal energy. And the process of transferring water by the streams is analogous to doing work. The process of adding water by rainfall is analogous to heating, and the process of evaporation is analogous to cooling. Note that the only quantity of interest is water, just as the only quantity of interest is energy in a thermal case. An examination of the change in amount of water in the pond tells us how the water got there. Not only the fact that the water is there, but how the water got there. So the terms rain and evaporation refer only to methods of water transfer, just as the terms of heating and cooling refer only to methods of energy transfer. So here we go. The pond is the system. The amount of water in the pond is energy of the system. Water transfer through streams, so water coming in by a stream is work in. Water leaving by stream is work out. Water coming in by rain is Q in. Water leaving by evaporation is Q out. So here is the system, right? This is my boundary around the water, right? As I'm drawing that imperfectly, right? So this is the amount of internal energy, which is water. This E system is the amount of water contained, and a water level indicator tells you basically how much energy is there. I have water coming in, crossing the boundary into the system by work, which is the stream. I have water leaving by this stream, which is work out. And then I have heat coming in, giving it energy by rain coming in, causing the water energy level to increase. And then I have water evaporating, analogous to Q out. That is basically what a first law is. It's equating the change in energy of the system in relations to how energy is being transferred in and how energy is being transferred out. So I hope that's helpful. Last part I want to cover in this lecture, and I think this is actually the last slide. We're going to be doing example problems in further in another video, but this will be the last slide for this particular video. Looking at energy conversion efficiencies or performance, right? So we're eventually going to be getting into calculations also of efficiency. And efficiency is an indicator of how well an energy conversion or transfer process is accomplished, right? And the basic the basic basis for any performance ratio is the desired output. Excuse me, I'll erase that extra line that was just drawn. The basic premise for quantifying any performance ratio is the desired output over the required input. Right, so desired output over required input. That is basically going to be the whole basis of how we compute efficiency and performance. So more of that to come at a later time. I'm going to go ahead and end the video here. This will end the lecture portion of chapter 2. The next video will go into example problems related to this chapter.